Hello, and welcome to Linear Algebra. This is lecture 31 on singular values. Right, so last time we talked about the QR decomposition. And I mentioned this is a useful factorization when you want to talk about solving equations, for example. And this is very stable compared to, for example, just inverting an invertible matrix, which might be great in theory, but might in practice have stability problems. You might have very small eigenvalues for A, which means that they become very large changes in A inverse. So continuing with the theme of wanting to understand a linear map by picking like the best basis or the best factorization or things like that, we're looking for the best representation of a linear map between V and W. Now, we've given one answer for this. You could say two. Diagonal matrices are obviously the best representations, right? But to have a diagonal matrix, well, if you have two different vector spaces, then you can always achieve that trivially because you can pick a basis for V and a basis for W. So in fact, let me go ahead and remind you of a result we've already shown. If V and W are finite dimensional and T is a linear map between V and W, it is always possible to choose bases for V and W such that the matrix associated to T with respect to these bases has some ones on the diagonal, right? The number of ones is equal to the rank of T, and all other entries are 0. Okay, so we've basically put all of the work into the bases, and this tells us nothing about T other than the rank of T. Okay, so fair enough. Now, another case where we've talked about the best representation is when you're mapping from a vector space to itself. In that case, we said, well, you could ask that you use only one basis. And okay, then you can ask for your map to be diagonal. And it's a much stricter, it's a much harder thing to achieve. If you're going to pick the same basis on both the domain and the codomain and end up with a diagonal matrix, then we've seen that you have to have an eigenbasis of your linear map. So that's difficult because not all linear maps have eigenbases. We found one way around that. When we're working over an algebraically closed field, such as the complex numbers, then if you have a linear map from a vector space to itself, you can ask for a single basis in which your map will be represented by an upper triangular matrix, and this you can always achieve. Right? So as long as you're over an algebraically closed field, you can always arrange for one basis to give you a upper triangular matrix or lower triangular, the completely equivalent theory. So the changes we want to make now is we want to allow different vector spaces, or if you're thinking in terms of matrices, non-square matrices, But now we have inner product spaces. So we're going to demand that you don't pick arbitrary bases. Here, we're going to demand that you pick orthonormal bases of V and W. And that's going to give us more information. So we're going to end up with a diagonal matrix, not necessarily ones on the diagonal. And the values that we end up with on the diagonal are going to be really important. Those are the singular values, giving us the name of today's lecture. So let me write that down. Demanding that the bases be orthonormal makes the diagonal values, which won't just be 1, more significant. We call them the singular values of T. One way of thinking about these is that they give you a replacement for eigenvalues. And that's important if we're working with different vector spaces, because eigenvalues are only defined when you're going from one vector space to itself. But singular values don't need that. Moreover, the singular values are going to be really important in applications. So they're going to play a very similar role to eigenvalues in applications to things like principal component analysis. We talked about principal component analysis when we talked about eigenvalues. Singular values are going to be a similar tool, for example, for data compression. I'll talk more about that after the lecture. Today's lecture, we want to set up some of the theoretical framework for these. So we're going to start with a lemma whose proof is a bit technical. Lemma says that if V and W are, so let V, W be finite dimensional inner product spaces, and let T be a linear map from V to W. So first, if E is a unit vector in the vector space V, such that the operator norm of T is equal to the norm of T of E. So remember, there always are such unit vectors. And now you pick any vector U in V, then these two vectors will be orthogonal precisely when T of U and T of E are orthogonal. Okay, so this is not at all obvious or immediate, right? In general, this being true does not imply this. So it's going to be, because this vector E is very special compared to T, relative to T. Then part 2, we're going to show that the subset U, consisting of all of the vectors in V, such that the norm of T of U is equal to the operator norm of T times the norm of U, is a subspace of V. Okay, so notice this is surprising. because this equation is not a linear equation, right? We're using norms here, and norms are not linear. In particular, the norm of a sum is not the sum of the norms. So this is a surprising result. Of course, we're going to prove it using part one. And this is going to be very useful when we talk about singular values. Jumping ahead a little, the operator norm of t is going to give us the first singular value of t. So this is, if we think of singular values as being like eigenvalues, then this is like the eigenspace corresponding to the first singular value. And so it's important that we figure out that it's a subspace. Okay. So the proof of this is going to be a little bit technical. The main tool, or the main idea you should have, is that this is an extreme equality, right? So we know that in general, if you have any vector u, then the norm of t of u is bounded above by the operator norm of t times the norm of u. So if you have a unit vector, then we know that the norm of t of e is bounded above by the operator norm of t. And so to have this equality is an extreme condition. So it's exactly that that's going to make parts one and then part two true. Okay, so let's start working on the proof. So let's introduce notation. Let's just let sigma be the operator norm of t, which I'll remind you is defined as the maximum of t of v when v varies over all unit vectors in the vector space v. And this operator norm satisfies that the norm of t of v is bounded above by sigma, so the operator norm, times the norm of v. It's true for all vectors v. Okay, so first, if sigma is equal to 0, so if the operator norm of t is 0, well, then t of v is equal to 0 for all vectors in v, and the lemma is true. Right, so if we're working with the 0 map, then this side is equal to 0 for all vectors, so this equality is always true. And here, those vectors u, so that the operator norm of t of u is equal to the operator norm of t times the norm of u, well, since this is always 0 and this is always 0, if t is 0, then this equality holds for all vectors in v. And so u would be all of v, and so it's definitely a subspace of v. So if the operator norm is 0, then there's nothing to prove. It's all easy. So let's assume sigma is not 0. So now the idea, before I start writing down inequalities, if you have a vector in U, so that t stretches v as much as possible, then perturbing v orthogonally needs to perturb t of v orthogonally. Right, that's what part 1 says. And the point is that otherwise, we'd be able to find a vector that T stretches more than V, right? So the idea is the same as what we used when we talked about orthogonal projections, right? When you look at a point not on a line, and you look for the closest point on the line to the one you're looking at, then it has to be the one that's the one joined to this point by something orthogonal to the line. Because if the segment joining the point to the line was not orthogonal, then by moving the point along the line, you'd be able to make this distance smaller, right? So it's the same idea here, just slightly more complicated geometry. Okay, well, let's carry this out. So now suppose that we have a vector u orthogonal to E, and let's give ourselves a scalar which we're going to carry around through the computations and not choose it until when it's convenient. Okay, so let's just have right now a scalar to be determined later. And let's consider the norm of T of E plus A times U. Right, so we think of perturbing the vector E in the direction of U, some amount, maybe it's small, A. Right? And it's useful to work with the norm squared, because the norm squared is easy to write in terms of the inner product. Right? It's just the inner product of this vector with itself. If we can expand that out using linearity in the first entry and conjugate linearity in the second one. So I'm not going to pull out any scalars. At the moment, I'm just pulling out sums. So we can write this as the sum of these four terms. Okay, so that's norm of T of E squared plus the real part of 2 times the real part of T of E paired with T of AU. Right, so notice that's because this term and this term are almost the same. It's just that the order is switched. We know that switching the order is the same as putting a complex conjugate. So what we have here is the sum of this number and its complex conjugate. And if you take a complex number and add its complex conjugate, you get 2 times the real part of that complex number. And then the norm of T of AU squared. Okay, and now T of E is, by assumption, equal to the operator norm, which at the moment we're writing as sigma. So I can write this term, so I'm going to say greater than or equal, this term is sigma squared. I'm going to keep this 2 times the real part. I'm going to go ahead and pull out the A. Pull out the A. Right, it comes out with a conjugate, but that's not a big deal. Right, and then I'm going to leave out this term, and that's why I get a greater than or equal to. Okay, on the other hand, the norm of T of E plus AU squared is bounded above by sigma squared times the norm of E plus AU squared. This is because for any vector V, T of V is bounded above by sigma times the length of V. So applying that here, we get this inequality. And now we can use that E and U are orthogonal to each other to bring in the Pythagorean theorem and say this is the norm of E squared plus the norm of AU squared. And then since E is a unit vector, I can write this as 1, and then I can pull out mod A squared there. And so I get this. And now if we combine these, right, so I know that this number is bounded below by this, and it's bounded above by this. So in particular, I know that this is less than or equal to this. Right, so I have sigma squared plus 2 times the real part of A bar T of E T of U is bounded above by sigma squared plus sigma squared mod A squared norm of U squared. Okay, and I can cancel these sigma squared. And so now I have that 2 times the real part of A bar times this inner product is bounded above by this. Okay, so now I'm going to choose A so that this product is a real number, and that'll allow me to remove this real part. So let's choose A equal to T of E times T of U times some epsilon. So that A bar times T of E, T of U inner product is equal to the modulus of T of E, T of U inner product squared times epsilon. Right, and here epsilon is going to be positive to be determined. So then we have, okay, so then this inequality, so the left-hand side now becomes 2 times, and here we said that this product is equal to this, which is a real number, so I don't need to put that real part. I'll just get modulus T of E, T of U inner product squared times epsilon is bounded above by sigma squared. And now this, what's this? A modulus A squared, well, that's, here's A. Here's A, so I take its modulus squared, so I get modulus of T of E, T of U squared, epsilon squared, norm of U squared. Okay. Now, here you might be tempted to divide by this guy to cancel it out, but that would not be good because, in fact, we're trying to show that that's 0, right? So in particular, dividing by it would not be allowed. Instead, let's just move everything to this same side. So let's put everything on this side. So we'll have 0 less than or equal to, okay, and we're going to have a common factor of this modulus T of E, T of U inner product modulus squared. And then we'll have this epsilon, and then we'll have, so from here, sigma squared times epsilon norm of U squared minus 2. Okay. Okay, but now this is true for all epsilon. right? I get to pick epsilon to be any positive real number I like, and this will be true. Now let's think about that. This says that this number is always greater than or equal to 0, right? Okay, well now this is greater than or equal to 0. This is greater than or equal to 0. This factor, though, whether or not it's greater than or equal to 0 depends on epsilon, right? So we have sigma squared, that's fixed. We have norm of u squared, that's fixed. And then we have this 2, right? Now, I don't care how big sigma squared is and the norm of u squared is, right? That can be 10 billion. If I pick epsilon small enough, right, like 1 over 10 billion, then this product will be smaller than 1. So if I pick epsilon small enough, I can make this factor negative. And if this is negative, then its product with these numbers is going to be negative unless these numbers give us 0. Epsilon is not 0. So the only way that this product could be 0 for epsilon such that this is negative is if this is 0, right? So since this is true, for all epsilon positive, we must have that the inner product of T of E with T of U is 0, right? And that's what we wanted to show. Okay, so again, this proof is proof by contradictions, and the contradiction takes a while to get to. But just remember, this is the idea. If we didn't have this inner product equal to 0, then we'd be able to choose U so that this was smaller than sorry, it was larger than its maximum value, and that's a contradiction. Okay, in any case, that proves part 1. Next, for part 2, we want to show that all of the, when you look at the set of all of the vectors where T of V is as large in size as it can be, then you get a subspace. Okay, so to show that something's a subspace, remember, we want to show 3 things. We want to show that it's not empty, so it contains a 0 vector, for example. We want to show that it's closed under scalar multiplication, and we want to show that it's closed under vector addition. So the first 2 parts are easy. So notice the 0 vector is definitely U. Excuse me. Also, if A is a scalar and U is a vector in capital U, then A times U is in capital U, right? That's also easy because here you would pull out, well, so first A would get pulled out to here, and then it would get pulled out to here in modulus, and A would get pulled out here in modulus, and so both sides would change by the same. So that's easy. So just need to show that if U1 and U2 are in capital U, then U1 plus U2 is in capital U. Okay, so there's an easy case. So first assume U1 is orthogonal to U2. Then part 1 shows that T of U1 is orthogonal to T of U2. So we can use the Pythagorean theorem, right? Let's look at the size of T of U1 plus T of U1 plus U2. So T of U1 plus T of U2 modulus squared, norm squared, and then Pythagorean theorem tells us that's T of U1 squared plus T of U2 squared. And then because they're in U, each of those is equal to the operator norm of T times the norm of U1. So both squared plus operator norm squared times norm of U2 squared. And that's equal to common factor of operator norm of T squared times the norm of U1 squared plus the norm of U2 squared. And now we use the Pythagorean theorem again to write that as the operator norm of T squared times the norm of U1 plus U2 squared. And that's what we wanted to show, right? So you can take square roots of both sides and you end up with the operator norm, the norm of T of U1 plus U2 is equal to the operator norm of T times the norm of U1 plus U2, right? Just like we wanted. Okay, but what if they're not orthogonal? Well, you can look at the orthogonal projection, right? So in general, if they're not orthogonal, we can always write U2 as A times U1 plus W with W orthogonal to U1. Right, so remember we proved this right before we started talking about orthogonal projections. So A times U1 is the orthogonal projection of U2 onto the span of U1. Okay. All right, so let's do that. And let's look at the norm of U2 squared, of T of U2 squared. Okay, so T of U2 squared I can write as the norm of T of, well, that's AU1 plus W squared, and that's T of AU1 plus T of W squared. And by the Pythagorean theorem, I can write that as the norm of T of AU1 squared plus norm of T of W squared, which is equal to sigma squared mod A squared norm of U1 squared plus norm of T of W squared. On the other hand, T of U2 squared is equal to sigma squared times the norm of U2 squared, which I can write as sigma squared times the norm modulus of A squared times norm of U1 squared plus norm of W squared. Right, and now if we combine these, so combine this one with this one, we get that the length of T of W squared is equal to sigma squared times the norm of W squared. So W is in U, and hence U1 plus U2, which is 1 plus a u1 plus w is in U. Okay, and okay, so that proves part 2, and that finishes the proof of the lemma. Okay, wonderful. So now we're ready to show that any linear map has a singular value decomposition. Okay, let V and W be finite dimensional vector spaces with inner products. And let T, linear map from V to W, be a linear map of rank R. So the claim is there are orthonormal bases V1 through Vn of V, W1 through Wm of W, and numbers sigma 1 greater than or equal to sigma 2, and so on down to sigma r greater than 0, such that T of Vj is equal to sigma j Wj for j between 1 and r, and 0 if j is greater than or equal to r. Okay, the numbers sigma 1 through sigma r are called the positive singular values of T, right? So these are the positive ones because often the singular values of T are thought of as these, and then some zeros to fill out. Right. As I mentioned, when we talk about matrices, the matrix associated to T with respect to these bases is only going to be non-zero on the diagonal, but these R numbers might not cover all of the diagonal, so you fill it out with zeros, and those are sometimes also considered to be singular values of T. So we'll call these the positive singular values, and if we want to talk about singular values including some zeros, we'll be specific about that. The vectors also have names. So let me point out that there's a lot of ambiguity in these vectors. So these are not at all unique, but these vectors are called the right singular vectors of T, and the W's are called the left singular vectors. of T. So again, this is analogous to talking about eigenbases. It's just that we have a basis of V and a basis of W, and there's no need for them to be the same. V and W don't need to be the same. And so here we're calling them V. That's with respect to this decomposition, because just like there can be many different eigenbases, there can be many different choices of right singular vectors and left singular vectors. The singular values, however, will be well defined. Those don't depend on any choices. Okay, so let's prove this. So for the proof, we will construct the bases V1 through Vn, W1 through Wm, one vector at a time. Okay, so first, let S1 be all of those u's in capital V such that the norm of u is equal to 1. Right, so just the unit vectors. And choose V1 in S1 such that the norm of T of V1 is equal to the operator norm of T. Okay, so as we mentioned at the beginning of the lecture, we've seen that you can always find a unit vector equal whose length, after mapping it with T, is the operator norm of T. Okay, if this value is 0, so if this operator norm vanishes, then T itself is 0, it's the 0 map. And the theorem holds. Right. If T is a 0 map, then there's nothing to prove, right? You can pick any orthonormal basis of V, any orthonormal basis of W, and this will hold. Right, with R equal to 0. Otherwise, so if the map is not identically 0, then let's call sigma 1 the size of this vector, so that is to say the operator norm of T. And let's pick W1 to be 1 over sigma 1 times the vector T of V1. Right, this is a vector in W. It's a unit vector, right, because sigma 1 we're dividing by the norm of T of V1, right? So T of V1 divided by the norm of T of V1, that's a unit vector. Okay, so let's say thus T of V1 is equal to sigma 1 W1, and the norm of W1 is equal to 1. Right, so check. That's our first V1 and our first W1, and this property holds. Okay, great. So next, let S2 be all of the u's in V so that U is orthogonal to V1 and the norm of U is equal to 1. Right? So before we were looking at all of the unit vectors, now we're looking at all of the unit vectors that are orthogonal to the first basis vector we've chosen. Okay, and choose a vector V2 inside S2 such that the norm of T of V2 is equal to the maximum of the norm of T of U when U is allowed to be any vector in S2. Right? So S2 is a closed and bounded subset of a finite dimensional vector space. So we're guaranteed by analysis, by calculus, that the maximum of this continuous function is achieved somewhere. There is some vector where this value is as large as possible. Now, if this value is 0, then T vanishes on span of V1 orthogonal complement. Right? So if, when you look at unit vectors that are orthogonal to V1, the largest possible value of the norm of T of V is 0, then your map is just identically 0 here, and so it's identically 0 on the span of this, and the span of this is just all of the vectors that are orthogonal to the span of V1. So in this case, we can extend the list V1 to an orthonormal basis. Of V, we can extend the list that contains the single vector W1 to an orthonormal basis of W, and the theorem holds. Right. So if T vanishes on the orthogonal complement of V1, then, well, you've already achieved this up to the rank of T was just 1, and then by extending the basis to be or whatever orthogonal basis you want, orthonormal basis you want, this is going to be automatic. Okay, on the other hand, if this maximum is not equal to 0, call that value sigma 2. Make the norm of T of V2 and W2 can be the vector 1 over sigma 2 times T of V2. This is a vector in W. Okay, so here T of V2 is equal to sigma 2 W2, right? By definition of W2. W2 is a unit vector. And by the lemma, so let's say by part 1 of the lemma, the fact that V2 and V1 are orthogonal to each other implies that T of V2 and T of V1 are orthogonal to each other, i.e. W2 and W1 are orthogonal to each other. Right? So check. That's what we want for 2. So we've carried out a construction of V1 and V2, W1 and W2, sigma 1, sigma 2, so that this holds for those choices. So you can see where we're going. Now we're going to assume inductively that we have constructed V1 through Vk inside V orthonormal such that T of V1 through T of Vk inside W is orthonormal And we've set sigma 1 to be the norm of T of V1, and this is greater than or equal to sigma 2, which is the norm of T of V2, greater than or equal, and so on, until sigma k, which is the norm of T of Vk. And that's strictly positive. Okay, inductively, if we've gotten this far, then we define Sk plus 1 to be all of the u's in V, so that u is orthogonal to the span of the list of orthonormal vectors in V, and norm of u is equal to 1. And then we choose Vk plus 1 in Sk plus 1 such that the norm of T of Vk plus 1 is equal to the maximum among all of the vectors u in Sk plus 1 of the norm of T of u. Right? If this value is 0, then T vanishes on the orthogonal complement of the span of V1 through Vk. So the rank of T is k, and we can complete V1 through Vk to an orthonormal basis of V. We can complete W1 through Wk to an orthonormal basis of W, and the theorem holds. Right? The sigmas would be all of the positive singular values of T, and the orthonormal bases you end up with give you the singular vectors. Right? Notice the clear lack of uniqueness. I don't care how you extend this set, this list, to an orthonormal basis of V. Any orthonormal basis extending this one will work. Okay, and if this value is not 0, then we set sigma k plus 1 to be equal to this value, so norm of T of Vk plus 1. We set Wk plus 1 to be 1 over sigma k plus 1 T of Vk plus 1. Right, and iterate. Okay, well, so that gives us a process, and this process must terminate after R steps, where we call R is equal to the rank of T, right? Because eventually the V's will be such that their images, so the W's, W1 through WR, will be an orthonormal basis of the range of T. And then after that, you're going to be in the case where the value, the maximum value on the sphere is going to be 0. And so then you can just complete an orthonormal basis if you have it, if you don't already have an orthonormal basis. Okay. So when we talk about a singular value decomposition, let me just say a singular value decomposition of T consists of the bases, so V1 through Vn of V, W1 through Wm of W, and the singular values. Sigma 1 through sigma r, the positive singular values. There can be a lot of choice. In the bases, but the singular values are always the same. Now, I've said that a couple of times, but it's not obvious. Certainly, our process for constructing these bases in the proof, that process would definitely give you an unambiguous list of singular values. But who's to say that some other way of constructing a singular value decomposition wouldn't give you other singular values? So this requires proof. So here's the theorem. So let's let V and W be finite dimensional inner product spaces. And let T be a linear map from V to W of rank R. Okay, so suppose you did two different singular value decompositions. Suppose there are orthonormal bases, V1 through Vn, and V1 tilde through Vn tilde of V, and there are orthonormal bases W1 through Wm and W1 tilde through Wm tilde of W, and real scalars. Sigma 1 greater than or equal to ... sigma r strictly positive, and sigma 1 tilde greater than or equal ... to sigma r tilde greater than 0, such that T of Vj is equal to sigma j Wj for j between 1 and r, and 0 otherwise, so j greater than or equal greater than r. And T of Vj tilde is equal to sigma j tilde Wj tilde for j between 1 and r, and 0 for j greater than r. Okay, then sigma j is equal to sigma j tilde for all j. Okay, so the theorem says exactly what we've been claiming. If you carried out a singular value decomposition of T in two different ways, then the vectors, could be very different, but the singular values have to be the same. Okay, so let's prove this. The proof is not very long. So notice that for any vector in V, we have T of V. Okay, well, we have an orthonormal basis. So let's just work with the first orthonormal basis. I can write T of V as T of sum, j goes from 1 to n, of aj vj, And then because t is linear, I can pull out the sum and the AJs. So I just end up with t of EJ. But t of EJ, I know, is equal to sigma j WJ. Right? So by the Pythagorean theorem, the norm squared of t of E is equal to the norm squared of this sum AJ sigma j WJ squared. Right, let me mention, of course, we know what these AJs are, right? Because it's an orthonormal basis. So each of these AJs is just the inner product of V with Vj. But I don't need that for this proof. Okay, so here, by the Pythagorean theorem, since these WJs form an orthonormal basis, this is equal to the sum, j goes from 1 to n, of the modulus squared, AJ sigma j. Well, so without skipping a step, this would be this. So Pythagorean theorem tells us that. And then since the WJs are unit vectors, this would be the sum of the moduli squared of AJ sigma j squared. And the sigma j's are positive real numbers. So I can write this as sigma j squared size of AJ squared. Okay, and in particular, this is bounded above by, if I replace all of the sigma j's with sigma 1, right? So norm j goes from 1 to n of sigma 1 squared by mod AJ squared. Actually, let me point out that here, I could have stopped the sum at r, because after the rth one, these are all equal to 0. I could have done that already. Over here. And so the sum, I only have to go as far as r. Because all of the other ones are equal to 0. Okay, but in any case, I can replace all of them by sigma 1, and then I can pull out the sigma 1 as a common factor. This is the sum j goes from 1 to r of mod AJ squared. This is bounded above by sigma 1 squared times the sum of all of these AJs squared, and that's equal to sigma 1 squared times the norm of V squared. And hence, the span of the VJs such that norm of T of VJ is equal to sigma 1, right? We can recognize this as U from the lemma. So this would be all of the V's in V such that size of T of V is equal to the operator norm of T times the norm of V. Okay, so from the lemma, we know that this is a subspace of V, right? From this computation, we see that if you have a vector here, so that the norm is equal to the operator norm of T times the norm of V, right? So sigma 1 is the operator norm of T, right? So, yeah. Well, or it will be. Let's say you don't know that. You just know that sigma 1 satisfies this, right? So this is a subspace, and the largest that T of V can possibly be, we see here, right, since this is less than or equal, is sigma 1 squared times the norm of V squared. Now, if you plug in V1, then of course you just get sigma 1 squared times the norm of V squared. So sigma 1 is both the largest multiple by which T of T can change the norm of V, and it is achieved. So it is indeed the operator norm of T. And if you look at all of the vectors that satisfy this equality, well, that's where this side is equal to this side. And if this side is equal to this side, that means that all of the times when I replace equality with less than or equal, I actually had equality. So things that I'm dropping were actually not there at all. So if we look at this one, we said that every sigma j could be replaced with sigma 1, right? And you got no smaller. Now we're saying that actually nothing changed. So that means that the coefficients aj were all equal to 0 unless j has sigma j equal to sigma 1, right? So that means that the v's for which you have an equality here can be written using only the vj's whose sigma j is equal to sigma 1, right? So that means precisely that if you look at all of the vj's whose norm is equal to sigma 1, norm after applying t is sigma 1, then that gives you a basis for this space. Okay, so in particular, let's point out, so sigma 1 is equal to the operator norm of t and repeats dim u times. Applying this argument inductively to t restricted to u perp, yields a theorem. Right, so the point is, I could have done this computation using either set of singular vectors and singular values, right? So here I used the v's, w's, and sigmas, but I could have used the v tildes, w tildes, sigma tildes, and I would have reached the same conclusion, that the first singular value is actually equal to the operator norm of t, and it repeats dimension of u times, right? So this is true for sigma 1, so it's also true for sigma 1 tilde. Okay, but now if you work with t restricted to u perp, then its operator norm is going to be sigma 2, and it's going to repeat dimension of, call it u2, where u2 is going to be this, but you've replaced v with u perp and t with t restricted to u perp, right? So this means that you can determine sigma 2 just in terms of operator norms of some operator, this operator, t restricted to u perp. And so that will show that sigma 2 is equal to sigma 2 tilde, and continuing in that way, you get the theorem. Okay, so we'll stop the lecture there. Feel free to stop watching now. I thought I'd just mention some context. I'll just talk a little bit more about how you use singular values and singular value decompositions. So next time, we'll be talking about singular values decompositions for matrices. So one of the things we're going to show is, if I give you a matrix, how do you actually compute the singular values? Because here, finding these operator norms or whatever, that seems more difficult than finding eigenvalues. And so that would make this decomposition less useful or less practical, perhaps, than looking for an eigenbasis. But in fact, one of the things we'll show is that singular values are closely related to eigenvalues. So a singular value of a matrix corresponds to an eigenvalue, say of a matrix A, corresponds to an eigenvalue of A star times A, where A star is the adjoint of A. So finding singular values is not going to be any harder than finding eigenvalues. They're also closely related to things like data compression. So another thing we're going to show next time is that if you have a linear map of rank capital N, and you want to approximate it with a matrix of rank K, then the best thing you can do in a technical sense, in a provable sense, the best thing you can do is just keep the K largest singular values. So this is used a lot in applications all over science. So in psychology, sociology, climate science, astronomy, data science, image processing, and machine learning, for example, all of these fields use singular value decompositions. And mostly they use this data compression scheme. So, for example, let's say that you had an image on a digital screen, right? So you have a bunch of pixels, and to each pixel, you're associating 3 numbers, right? A saturation value for red, green, and blue. And these go on a scale from 0 to 255, right, usually. Keeping all of this data would take a lot of memory, right? Especially if you imagine like a game or a movie or something where the images are changing rapidly. So you'd want to have a lot of different images per second so that it looks realistic, quote unquote. And so having this much data several times per second, that would eat up a lot of memory and processing time. So instead, what you want to do is approximate with a matrix of lower rank. So you don't want to keep track of all of the values of all of the pigments, but just enough so that it looks right. Same thing if you have like a scan and you want to save it with different qualities, but you want it to be recognizable. So what you want to do is approximate it with something in an intelligent way. So you can think of the singular values as telling you how well your approximation works. If you have a matrix of lower rank, but the singular values of that matrix, which will just be a subset of the singular values of the matrix you started with, make up 90% of the sum of the singular values that you started with, then you could think that you have like 90% of the information of the image. And often the singular values drop off quickly, right? So, you might have 1,000 singular values for your original image, but you only need to keep the first 60 to get a really good approximation of your image. So that's a huge saving in memory. I've added a link to the course webpage to an article where you can see examples of how this works. So if you go to the course webpage and then you click on the links tab, then there you'll find this article. Okay, so let's stop there and pick it up from there next time.